So shall I introduce? Everyone can hear me?
Yes, we can hear you.
Yeah, okay, perfect. So for about 2.5 months, we studied over the Huybrechts books, Huybrechts complex geometry book about like to introduce to the complex geometry. We went through the basics with Esma about defining different operators and like covering some main theorems like Hard Lefschetz Theorem, Serre duality. And at the end, I think we managed to do a good job on that. So now she will present you what we did for the last 2 months.
Thank you, Demir, for introducing this. I will today tell you about the complex geometry. So I start with introducing complex manifolds, and then I would briefly discuss differential forms, and then we will move on to some particular type of complex manifolds called Kähler manifolds, and then we will see that by applying Hodge theory on Kähler manifolds, we get some very beautiful results. Actually. So, and at the end, I will present you the famous Hodge Conjecture. Before I will give you the definition of complex manifolds, I will briefly discuss topological manifolds and differentiable manifolds. Now, topological manifold is that you have an open cover of your set, and then you have coordinate maps. That's mapping from, let's say, U alpha to the, if you have a real manifold, to Rn, and then you want your transition functions to be continuous. And in differentiable manifolds, you want them to be differentiable. So in the definition of complex manifolds, it's not really that different. This time, it's transition functions are this time holomorphic. Now, what I mean by holomorphic, it means complex differentiable. So an example would be the torus. Our friend torus is a complex manifold. Also, a classical example would be the projective space. You can think of it as a complex line like this. So now I will talk about differential form. Now we have a complex manifold, and we want to be able to do calculus on differentiate. We want to integrate, and then things that you integrate over your manifolds is called differential forms. I gave some examples. A zero form would be a smooth function on your manifold. A one form would be just a differential of f, and a two form on a three can be represented like this. And then now I will give you what is that fundamental form is. Well, fundamental form basically is a metric actually. Measures distances, areas, and volumes in higher dimension spaces. Before that, I need to introduce something called an almost complex structure. Now, it is an endomorphism of your real vector space, finite dimensional vector space, that has a scalar product on it. So an almost complex structure would be something that when you apply it twice, you get minus the identity. So you can think of like complex plane. You have points on your complex plane, and you multiply by I, you rotate by 90 degrees, and then when you multiply it by I again, you get the minus point. So you can think of it as a generalization of the multiplication by I. So I give the definition of fundamental form as this. It's yeah, basically it's a scalar product. It measures distances and areas. So there's a proposition that says what I just said. It just measures areas, volumes, curvatures. And then this proposition tells us that it is a two form and a one form. What is a one form? Is it has one holomorphic part and a one anti-holomorphic part. Now you can think of it as this. I can illustrate it. That would be the holomorphic part. That part would be the anti-holomorphic. So now I will introduce some linear operators. Now the Lefschetz operator just takes k forms to k plus 2 forms by just wedging with the fundamental form. The Hodge star operator is defined as this, but it just basically takes k forms to n minus k forms. So if you have a, let's say, 5-dimensional space and you have a 2 form, then if you apply Hodge star operator on it, you get a 3 form. The dual Lefschetz operator is defined in terms of Hodge star operator, so it's dual of the Lefschetz operator. And then I will present you some differential operators also. So we have the external derivative where it takes k forms to k plus 1 forms, and there's a partial del operator and del bar operator, but it takes forms.
Interesting. But it's for the required not specific matter it is not I will give direct solution. Madam,
Del operator takes PQ forms. PQ forms where they have P multiplied and Q multiplied, and they take them to P plus Q forms. And the del bar operator is defined as it takes PQ forms to P Q plus 1 forms, and I illustrated how they act, what they do. So now you have differential operators and linear operators, and it's not okay. So now we will introduce scalar manifolds. Now, why do we like them? Why do we study them? Because they have very rich structure, very rich geometry. So they are complex manifolds. They have a Riemannian metric, which makes a Riemannian manifold. They also have a symplectic manifold structure. What I mean by symplectic manifold, now you have a 2 form that is closed. Being closed means when you differentiate it, you get 0. So and it's non-degenerate. Non-degenerate means if you have our fundamental form and you omega v w is if it is equal to 0 for all w, then v must be 0 in some. Now I will give you the definition. Here we have a Taylor manifold is a Hermitian manifold where the metric, where the fundamental form is closed under the exterior derivative. So the simplest example would be the complex plane itself with the Euclidean metric, and torus is also a Taylor manifold, and the complex projective space is also Taylor manifold with the special metric. Locally defined as this, and you glue them together, get the global form. Now, we have defined a bunch of operators, but of course they're not enough apparently. You have the adjoint operators. This time, this star operator takes k forms to k minus 1. The D operator took k forms to k plus 1 forms, and they are defined as this. So we defined also the Laplacians in here. So now we have a lot of operators, as you know, and we wonder how do they behave. What are the relationship? What is the relationship with them? So in Kähler manifolds, they behave especially well because well, this is the brackets here, just it's a commutator. So if you know some group theory, if you take like bracket GH, it's just GH minus HG. So this being 0 means they commute. So Lefschetz operator commutes with del and del bar, and the dual Lefschetz commutes with del bar star and del star. And the nice thing is Laplacian just commutes with everything. And then I will present you the results of Hodge theory. When we apply Hodge theory, we get some very remarkable results on Kähler manifolds. It's actually because of the metric, the way the metric is defined. And before that, I need to define you one more object is called harmonic forms. They're just the kernel of the Laplacians. So yeah, they vanish under Laplacians. So now I will give you some results, as I said. So now we have the composition of K forms into PQ components. So if I give you a K form, you can write it as a sum of PQ forms. But the question is, can you carry this over to cohomology? So if you have a Kähler manifold, then yes, you can. Gitmeyecek bu arada. Yeah. Can we carry this over to cohomology? So if you have a Kähler manifold, yes, you can. So we get this by Hodge Decomposition theorem. So the Hodge Decomposition theorem tells us that you can the PQ differential forms have three parts to them. So this is the image of the vowel operator plus the harmonic part plus the image of this. So you have analogous decomposition of that with respect to the vowel operator. So the beautiful thing is here just this harmonic forms, space of harmonic forms, finite dimensional. Now this part, the PQ forms, differential forms are infinite dimensional. So you have a finite dimensional part of it that you can study and understand rather than movement. So if your manifold is moreover, if your manifold is Kähler, then their harmonic forms are the same as Dalbar harmonic. So as a corollary, you get that PQ harmonic forms are isomorphic to the PQ cohomology of this manifold. So you have actually this tells us that you can represent a cohomology, PQ cohomology class with a unique harmonic representative here. So if your manifold is Kähler, then you get the decomposition of cohomology. They are the same in this. Before doing the Hard Lefschetz Theorem, we need one more object. It's called the primitive cohomology. You can define as the kernel of the dual Lefschetz operator. So the Hard Lefschetz Theorem reveals some symmetry on the cohomology of the manifold. So if you're wondering why it's called Hard Lefschetz, basically Lefschetz proved it, but the proof turned out to be wrong, and then other people tried to prove it, and so it was hard even for Lefschetz to prove the theorem, so that's why it's called Hard Lefschetz. So here's the theorem that tells you the Lefschetz operator induces an isomorphism between n minus kth cohomology and the n plus kth cohomology. And you have a Lefschetz decomposition of the cohomology in here. Now, we present the Hodge conjecture. Hodge conjecture basically tries to relate the topological data to the algebraic data. So our topological data in this case are homology classes, and our algebraic data is the algebraic cycles. Now it's actually a generalization of Lefschetz 1-1 theorem that tells us the Picard group of X, map from Picard group of X to the one-half homology class, cohomology of this manifold is surjective. So it means that we can represent this topological object by a algebraic object. So the Hodge conjecture says that you can do that in higher dimensions also. It basically tells us that. Now I will illustrate this by a example. We have the complex, one-dimensional complex projective space. You can think of it as a Riemann sphere. So Picard group, I didn't tell you about what Picard group was. It was it's just the isomorphism classes of line bundles. Line bundles correspond to divisors, and divisors are basically just the formal sum of one codimension one spaces of your manifold. So if you have a plane, then your codimension one objects are lines. In this case, our dimension is one, complex dimension is one. In this case, they're just formal sums of points. So now I'll give you a fact of life that Picard group is just the integers. Then I will give you another fact of life that the second cohomology of P1 is the integers again. And then from the Hodge decomposition theorem, we decompose our cohomology into its parts. And then you see that H20 and H02 are just 0. And you get that H11 is actually equal to the H second cohomology of 1. And it was integers, so the conjecture is true for P1. So if you want, there are my references. And